Hi, I'm Jinhong Li from the Chinese University of Hong Kong. I'm going to present an in-depth analysis of cloud block storage workloads in large-scale production. This is a joint work with folks from Alibaba Group. Nowadays, more and more applications such as virtual desktops, operating systems, web services, and key value stores are moving to cloud. The cloud block storage systems allow cloud service providers to manage the large-scale physical storage clusters. Also, trace analysis in production environments is critical in the storage workload optimizations. We can also see that several field studies have analyzed the I/O behaviors of various architectures via analysis on block-level I/O traces. In particular, the public block-level I/O traces released by Microsoft Research Cambridge have received wide attention from researchers. However, the MSRC traces were collected from enterprise data centers more than a decade ago and may not necessarily reflect the actual I/O behaviors of today's cloud block storage systems. Therefore, we may need to collect traces from the real production cloud storage systems and perform the analysis on them. Cloud block storage systems should maintain quality of service guarantees such as low latency requests and fairness. Also, it should provide efficient resource utilization policies to improve endurance on storage devices. Therefore, we consider three aspects on the design considerations of cloud block storage systems. At first, we consider the load balancing across storage devices, which avoids the imbalanced traffic in different volumes and different time. Second, storage systems typically cache frequently accessed data to speed up I/O performance. We need to investigate how the caching design can leverage workload characteristics so that we can improve the hit ratios and boost I/O throughput. Third, enterprise storage clusters increasingly move to flash-based storage, which is sensitive to the varying workload patterns in both performance and endurance. Therefore, storage cluster management should address the variation of workload patterns to maintain high performance and endurance of the underlying flash devices. We consider such an architecture of a cloud block storage system. It comprises multiple volumes that host a mix of cloud applications. For example, the virtual desktops, operating systems, web services, relational databases, and key value stores. Each application is allocated with a dedicated volume. The cloud block storage system serves as a middleware layer that bridges the virtual volumes and the underlying storage clusters. The storage clusters provide physical storage space owned by the cloud service providers. Our conclusion is that we provide an in-depth study on the block-level I/O traces collected from a product of cloud block storage systems at Alibaba Cloud. The second contribution is that we analyze the cloud traces from Alibaba Cloud and the MSRC traces and compare their basic characteristics from a high-level perspective. On the trace analysis and I/O characterization, we provide the findings and their implications on three aspects: load intensity, spatial patterns, and temporal patterns. Finally, we have released our traces with billions of I/O requests and hundreds of terabytes of the I/O traffic. Welcome to use our traces to verify our findings and conclusions. We consider two traces, which we refer as Ali Cloud and MSRC in short. Ali Cloud are traces collected from a cloud block storage system deployed at Alibaba Cloud. They comprise block-level I/O requests collected from 1,000 volumes. They are over a one-month period in January 2020. Each request contains the volume ID, request type, request offsets, request size, and the timestamps. MSRC are traces collected by Microsoft Research Cambridge from a data center of Microsoft Windows servers with 36 volumes over a one-week period in February 2007. Each request contains the same fields as Ali Cloud traces, with the additional response time. We provide some basic analysis to compare the two traces from a high-level perspective. The table shows the basic information of the two traces. The reads and writes are measured as the number of read or write requests. The working set size is the amount of unique data accessed by the request. It indicates how much disk space is actually used by the applications. Ali Cloud has a larger scale in terms of the duration, the number of IO requests, the number of volumes, the amount of IO traffic, and the working set size of the volumes. We find that the reads span small working sets in Ali Cloud because reads span only 34.3% of the working set size in Ali Cloud, which is a small proportion. However, the corresponding ratio in MSRC is 98.4%. As for the write-to-read ratios, in the figure, we show the cumulative distribution of write-to-read ratios in each volume. We measure the write-to-read ratio as the number of writes divided by the number of reads in the volume. 91.5% of Ali Cloud volumes are write dominant, while only 53% of volumes are write dominant in MSRC. We find that the small size IOs dominate in both traces. On the left-hand side, we show the cumulative distributions of the read and write request sizes. 75% of the read and writes in Ali Cloud or MSRC are no larger than 64 kilobytes. On the right-hand side, we show the cumulative percentage of volumes with respect to the average read and write request sizes in both traces. As for the average request sizes of volumes, they are also small for most of the volumes. We study the activeness of the volumes and measure the number of active days for each volume. A volume is said to be active if it has at least one IO request. We find that a non-negligible fraction of volumes in Ali Cloud are active in short time periods. The figure shows the cumulative percentage of volumes with respect to their active days. For Ali Cloud, we find that 15.7% of the volumes are active for only 1 day. However, for MSRC, all volumes are active in 7 days. One possible reason for this observation is that some volumes support short-lived tasks in cloud applications. For the summary, we show the commonality and differences of the two traces. In both traces, the small IOs are dominant. For the differences, Ali Cloud has a larger scale in terms of the duration, traffic, the working set size, and the number of IO requests. Ali Cloud has smaller read working sets, which means that only a small proportion of the unique blocks are read, and most of the blocks are only written rather than read. Ali Cloud has some volumes which are active in very short time. Ali Cloud has larger write-to-read ratios compared to MSRC, and most of the volumes are write dominant. Now we come to the findings on 3 aspects. The first one is load intensity. In finding 1, we find that both traces are similar load intensities of volumes. We measure the load intensities of individual volumes in terms of the number of requests per second. The average intensity of a volume is defined as the total number of requests divided by the time elapsed between the first and last request of the volume. For the peak intensity, we divide the whole duration of the request of the volume into 1-minute intervals and find the peak intensity as the maximum number of requests per minute across all intervals. We plot the figures by sorting all volumes by descending order for 2 traces, and we find that in 2 traces, the average intensity and peak intensity are smaller in both traces. For finding 2, we investigate the burstiness of each volume by dividing the peak intensity by the average intensity. The figure shows the cumulative percentage of volumes with different burstiness ratios. We find that both traces have high burstiness in some volumes, especially in some volumes of Ali Cloud. The burstiness ratios can be larger than 1,000. However, The global burstiness ratios are not the case. The global burstiness ratios are smaller than 10 for both Ali Cloud and MSRC. For the third finding, we find that Ali Cloud has more diverse burstiness across volumes. Along with the descending order of average intensity, the peak intensity in Ali Cloud fluctuates rapidly. Also, there is a higher percentage of volumes with very low or very high burstiness ratios in Ali Cloud, but it is not the case for MSRC. In the previous findings, we investigate the load intensity by the number of requests in a short time. Now we investigate the inter-arrival time of the request. The inter-arrival time is measured as the elapsed time between two adjacent requests in a volume. A smaller inter-arrival time indicates larger burstiness in a short time. We find that both traces have high short-term burstiness from the perspective of their inter-arrival times of requests. To illustrate the results, we consider 5 groups of percentiles of inter-arrival times for each volume and draw the box plots for each group of percentiles for both traces. We find that both traces have a high number of burstiness requests, as indicated by large fractions of short inter-arrival times in the volumes. For example, the medians of the groups of these 3 percentiles are lower than 1.3 milliseconds, which is equivalent to a load intensity of at least 700 requests per second. After we investigate the inter-arrival time, we consider the activeness of each volume. We divide the traces into 10-minute intervals and examine the activeness in each interval. A volume is active in a 10-minute interval if it has at least 1 request in the interval. Concisely, we call a volume is read active or write active if there is at least 1 read request or write request in the interval. The 2 figures on the left-hand side shows the number of active, read active, and write active volumes throughout the trace periods in both Ali Cloud and MSRC. We find that at least 59.4% of the volumes are active throughout the whole trace period. The 2 figures on the right-hand side show the number of 10-minute active intervals. We find that more volumes are active in 95% of trace periods of Ali Cloud than MSRC, which shows a higher activeness in volumes of Ali Cloud. Then we compare the activeness in read and write separately. We find that the writes are the dominant factor of the determining activeness in both Ali Cloud and MSRC. The reason is that in both traces, the curves of active and write active almost overlap with each other all the time. We also find that if we remove write requests, the activeness drops rapidly. Figures on the left-hand side shows that the number of active volumes drops by more than 58.3% in Ali Cloud and 24.6% in MSRC. Until now, we have discussed about 7 findings on load intensity. Then we will turn to the part of findings on spatial patterns. At the first finding on spatial patterns, we investigate the randomness of each volume. We measure the randomness of each volume by calculating the percentage of random requests. We say a request to be random if the minimum distance between offsets of the current request and the previous 32 requests is smaller than 128 kilobytes. The figure on the left shows the cumulative distribution of randomness ratios. We can see that the randomness ratios of Ali Cloud is larger than those of MSRC. The figure on the right shows the randomness of the top 10 update intensive volumes in both traces. We can see that the randomness ratios in top 10 volumes of Ali Cloud is higher than MSRC. Some of them can even be higher than 80%. We will also introduce other 3 findings briefly about the spatial patterns. Finding 9 shows that reads and writes aggregate in small working sets, and writes are more aggregated than reads. Finding 10 shows that reads and writes tend to aggregate in read mostly, and write mostly blocks in Ali Cloud. MSRC shows stronger aggregation in reads but weaker in writes. Finding 11 shows that the update coverage is higher in Ali Cloud, and it varies a lot in different volumes of the two traces. Here we refer the update coverage to the ratio of the update working set size divided by the write working set size. For temporal patterns, we investigate the temporal relationship of the adjacent I/O requests. Finding 12 is an example of investigating the request after a write request on a block. We refer a read after write request to the read following immediately the write to the same block, and a write after write request to the write following immediately the write to the same block. We measure the time of a read after write request as the elapsed time between the adjacent read and write to the same block. The figure shows that both traces have large read after write time, but small write after write time. It indicates that the written block tend to be written again rather than read. Other three findings on temporal patterns are shown below briefly. In finding 13, we find that most of the read after read and write after write requests in Ali Cloud have large elapsed time. On the other hand, a non-negligible fraction of them in MSRC are short. In finding 14, we find that the written blocks have varying update intervals in both traces. We refer the update intervals as the elapsed time between two consecutive writes to the same block. Finding 15 shows the relationship of the cache miss ratios in two traces. We use 1% or 10% of working set size of each volume to simulate the cache behavior and use LRU policy to evict the blocks. We investigate the absolute reduction in miss ratios of the two traces and find that Ali Cloud has a higher absolute reduction. After talking about the findings, there are some examples of implications. For load balancing, we find that writes dominate in the activeness. Therefore, we should focus on optimizing the writes in Ali Cloud when performing load balancing. For cache efficiency, we find that it is viable to allocate limited cache resources to improve the I/O throughput. It is also viable to identify the read mostly and write mostly blocks. Disk-based read caching, write caching can absorb the writes, which can also help the cloud storage systems to improve the endurance of underlying flash devices. For storage cluster management, log structures or upper layer flash translation layers may optimize the performance on small and random I/Os. For the conclusions, we provide 15 findings in terms of the load intensity, spatial patterns, and temporal patterns. We provide insights from the findings on how to address the issues on load balancing, cache efficiency, and storage cluster management. We'll release our traces at this link. Welcome to download the traces to verify our findings and conclusions. Thanks for your watching. If you have any questions, please feel free to ask.